Hey Algebra 2, welcome. We are going to do 6-6 and we're doing scatterplots today. So a scatterplot is a type of data display that shows the relationship between two variables. So I think I'm going to keep referencing this graph here at the bottom. So this one was really good because, so the scatterplot are the points. They're these data points where somebody went out and they collected some data. And then the straight line we're going to learn is called the line of best fit. It's the line that estimates the equation that represents all the points shown. So correlation shows the relationship between two variables. Positive correlation might look like this. So we're in quadrant 1 of a coordinate plane. And we collected some data. And we plotted the points. We graphed it. And so, what is the relationship? So when x is small, your y value is small. As x get bigger, the y gets bigger. So what I would say is, as your x value grows up, your y value also goes up. This is like positive slope. Some data might show a negative correlation. So a negative correlation might look something like this. So when x is really small, your y value is really big. And as your x value gets bigger, your y value keeps getting smaller and smaller. So as the x value goes up, the y value is going down. This is like negative slope. Sometimes there is no correlation. Could you read my mind and tell me what this is going to look like? Just kind of random all over the place. There is no relationship between x and y. Next section is talking about the strength of the relationship between x and y. So the relationship or strength of the correlation is determined by how clustered or widespread the values are to the straight line. The straight line is what we would call the line of best fit. So the straight line that they drew here is the line of best fit. This graph is showing a very, very strong correlation because the majority of the points are really close to the line. Strong correlation means the majority of points are close to the line of best fit. Weak correlation, we'll just say points are not close to the line. So on here we have the equation of the line of best fit. So this is already in slope-intercept form. Y equals 1.6176x minus 2864.6. This is the equation of the line of best fit. So the equation and the word model is something that we're probably going to use interchangeably. So when it says, what does the model predict? That's code for, hey, go look at the equation and use it. This R value right here is what we call the correlation coefficient. Those of you that are going to go on to take a statistics class, you will certainly talk more about it. They decided that they would use the word or the letter R. Sometimes I've seen it as R squared. It's been a while since I've taken statistics. I can't remember why they chose that. The correlation coefficient judges how close or how far apart the data points are to the line of best fit. You want to think of it as like a grade. When you go to school, you want an A. So when you're looking at this number, the correlation coefficient, think, hey, I'm going to grade this like I'm going to school. A, B, C, D, F. So we want an A, which means that you are looking for a number that is 0.90 or larger. If you do some research and you get some data and you draw in your line of best fit and this correlation coefficient is only at a 70%, you probably don't want to be publishing your findings because that is not good in the world of correlation coefficients. All right, so we're going to judge this now. So, is the data showing positive, negative, or no correlation between the variables? Positive, negative, none. Positive. We have a positive correlation we're looking at. This says, what value does the model predict? Model says, hey, go use your formula or your equation for the concentration in the year 2000. Part of this section, you just need to pay attention and you need to read the labels. So on your x-axis, we have years. And so it's a little hard to read, but I know that that first one is the year 1970. And then we have 75, 80, 85, 90, 95, 2000, 2005, and 2010. And then the y-axis is measuring the concentration of carbon dioxide. So the first one is 300, and then it's counting up in 20s. 320, 340, 360, and 380. So if you have a graph, you should certainly try to estimate. So in the year 2000, so if you come up here, and then you follow it to the left, I'm expecting my concentration to be an answer between 360 and 380 because that's what my graph says. So my graph says it should be 360 to 380. This says in what year, and my x-axis right here is labeled with year. So this is saying, hey, I want you to plug 2000 in place of x. And so that's what I'm going to do, and I don't have room to rewrite it. 1.6176 times 2,000 minus 2864.6. You're going to plug that into your calculator. You're going to run the numbers. And if you did it correctly, you get 370.6 is the concentration of carbon dioxide in the air in the year 2000. All right, so that was called interpolate the data. So if you have, so any time between the year 1970 and the year 2010, this is a good formula. We could plug any year in for X, and we could get a pretty accurate answer. It could be a little naive to think that this data is going to go up and up and up in this kind of a straight line forever and ever and ever. Although it has for the last 40 years, but you should be very, very wary. If it says, estimate the amount of carbon dioxide in the year 2024, I mean, I would be super leery. That would be called extrapolating the data when it continues on and you're guessing or estimating a value outside of what is on your graph. All right, so on the next side, I'm about ready to define the line of best fit. So just to know that this is the line that we're talking about. Line of best fit is a line drawn on a scatter plot that represents the data. It should be in the middle of most points. The prediction equation is just simply the equation of the line of best fit. In the section that we're doing, it's mostly going to be in the form y equals mx plus b, although it is naive to think that all data is linear. It could be exponential, it could be quadratic, it could be a number of things, but ours is probably going to be linear. It's probably been a while since you've written the equation of a line of best fit. So this is some Algebra 1 review here. First thing you're going to do is find slope. So it says using the lower and upper limit, find the slope. You can do that. Substitute the slope and the point. So x1, y1 is a point that you know into y minus y1 equals m times x minus x1. So this is the equation of a line in what we would call point slope form. And then finally we're going to solve for y. All right, so on number 3 here, it says write an equation for the line of best fit. So the first thing you're going to have to do is you're going to have to draw a line in the middle of this data. All right, so it helps when you have, I'm going to go there. That one doesn't seem too bad. It might be a tiny bit low, so these points up here are a little further away from the line than these points down here. So maybe if it was a little bit steeper, maybe that would be more reasonable. But for today's lesson, this is completely reasonable. So once you have your line drawn, we're going to write the equation of this line. So the first thing that you need is slope. When you have a graph, so M is slope, I would think of using rise over run. That is a fantastic option. So the way that I drew my line, it hits my y-intercept right here at 30. And then it also looks like it's hitting this point at 60, 40. So from a graph, you can calculate slope by doing rise over run. So from this point up, I just went up 10 units. And then I started at 0, and I went over to the 60. And so the slope of my line is about 1/6. Well, you can do this if you want. If you can figure out your B or your y-intercept, that will make your life so much easier. So on this one, when I drew in my line, I made it start right here at the 30. So the equation of a line is y equals mx plus b. So now I know my slope and I know my y-intercept. So write the equation for the line of best fit. That is good. Part B says predict the y value when x is 16. All right, so it just tells you that, hey, plug 16 in for x into that equation and run the numbers. Clear. I've done this problem different every single time. One moment. Plus 30. My calculator gave me the answer as a mixed number. If yours gives it to you as a decimal and you choose to round it, if you use my numbers, your calculator might say 32.6 repeating, so 2/3 is the same as 0.6 repeating. All right, so when x equals 16, so that means it would be right about here. I would always fact check it against your chart. So if you go up and over, yep, I would believe that that was about 32. So all of this seems to be reasonable. So the SAT is coming up. Are you going to have to write the equation of a line on the SAT? Probably not, no. What I do think that you will have to do is more like problem number 4. So problem number 4 on the x-axis, so pay attention to your labels. The x-axis talks about the age of the driver. The y-axis talks about the number of accidents that they get in per 100 drivers. So it wants to know what is the trend that happens. So a 16-year-old, they get in like 23 accidents. The 19-year-old drops down to 15 accidents. So when you look at this, what could you say is happening over time? As your driver gets older, what is happening to the amount of accidents that they get into? It seems to be going down. Good. So which one of these choices, A, B, or C, matches that? As your driver gets older, the accidents go down. A matches that. That is probably all you're going to have to do with a scatter plot on the SAT. Number 5, Megan measured the height and petal length in centimeters of the flowers in her gardens. The data in the table, oh yeah, I changed it, no tables, but I just went ahead and plotted the points for you. Draw in the line of best fit. All right, so you're going to do your best. You're going to try to follow the majority of the points. You're going to try to have some equal amount of points above and below your line of best fit. That one looks pretty reasonable. So you have to write a description. So on the prior one, you could just do multiple choice. Now you have to write your own. So the x-axis is the height of the plant, and the y-axis is the petal length. So I would always start with the x. So as the plants get taller, what is happening to its petal length? Going up, going down, no relation. Going up. I said the taller the plant, the longer the petals. So I would always start with the x, related to the x. So maybe you said as the height goes up, the petal length goes up. That is fine. How long should a petal be if the plant is 25 centimeters? We aren't writing an equation, we're just going to estimate. So here's 25. If you go up and then you look to the left, it should be about how long? 5 centimeters. Perfect. Thank you so much.